Alright, hey guys. Today the plan is to do Kickstart. And yeah, well, right now we're just waiting for it to start. And whenever it does start, oh, okay. I guess that did start. Alright, so we're gonna read this. Charles defined the goodness. Alright, yeah, I'm just gonna jump into it. And actually first, should update the sub count while I'm reading the problem. Because why not? I'm not sure how well I'm gonna do. I should note that this round is at midnight, so this is gonna be fun. Okay. So it's not equal to that. Okay. Alright, so Cn2 and decay. Oh, nice. Oh my god, that's awesome. They added these, like, copy things. Okay. Let's see. Should be good. No reason it would not need to... Yeah. Okay. What? Oh, wait. Whoops. Okay, that was not good. Alright. Given a grid... Okay, segment is... segment of a row or a column. Alright, that's weird. Okay, so what's with that? Character index 1 to B. Oh, wait. Oh my god. Okay, that's stupid. Did not read the problem right and the samples did not help. Okay. Yeah, alright. Damn it. Okay, that's stupid. Should not... That should not have happened. Okay. That's a dumb penalty. Alright, we have a... Cool. Segment is called good if all cells contain only one. An L shape is an unordered pair of segments, so they're perpendicular to each other. The endpoint must be the same. Yeah. Wait, what's wrong with that one? The length of the longer is twice the length of the shorter. Exactly twice. So we're counting the number of L's. Alright, we fixed the pivot. Okay. How's this gonna work? let's just do this. Do something stupid, doesn't really matter. But yeah, that mistake in the beginning is what happens when you read problems too fast. So basically what I'm doing is I'm counting the number of ones we have in all of the directions, and then yeah, so this is n minus 1, I is greater than 0. Alright, now for each row, okay, so how'd this work? So given a certain number of ones in some direction and some other direction, we need to figure out how many L's we can have. Segments will have length at least 2. Okay, so it's min, so it should be floor of A over 2. Or no, wait. A and then right, and so let's see, how does this overcount? So it overcounts 1, 2 maybe. If A is greater than equal to 1, or let's see, if B is greater than 1 minus 1. Yeah, because we overcount maybe the case of 1 and 2. Every other thing should be valid. Yeah, okay. Sounds good. Let's see. Okay, so this should be 3, this should be 2, this should be 1, this should be 0. Oh, I count. One and 12. Alright, so let's see. Alright, so let's first look for mistakes here. So here we go from 0 to m, and we go from m to 0. Then we go from, oh wait, okay, we have to reset it. If not grid ij c equals 0. Yes, because we're counting the number of running ones, not the number of ones above or below. Okay. Let's see, this is too hard to track. So I think this is good. We look for all directions 0, 1, 2, 3. Yes, and we say, so assuming the first one is the lower one, we can have anything up to that or that. And we overcount by a bit, possibly. Let's see, let's just do one more. 1, 2, 2. Good. 1, 4, 2. Cool. We got rid of the counts. Okay. Barbara got really good grades, so her parents decided to gift her with a pet rabbit. She built a house which can be seen as a 2D grid. The result to jump, so she stacked several boxes. Each box is a cube. Yeah. She can add boxes on top of them. Okay, how's that gonna work? So do some sort of like BFS thing, I guess. 2 times 10 to the 6th. How many tests are there? To use 100, 40-second time limit. So we can iterate through 100 times 2 times 10 to the 6th, I guess. I don't know why they'd have it be that large though. Okay, so let's see. And then why I'm using different. All right. So we're not sure how to explain this on the fly, but basically we're doing some sort of BFS-like thing, where we pick the largest one, and then we sort of like say that all of these have to be at least one within it. If they're the same height, then it's fine. If not, then yeah. Rec ij is equal to mat ij. Actually, I can put this here. V dot pushback sort. Sorry again for the lack of commentary. It's not the most interesting thing. I'm just sort of trying to be fast here. I want to get a good rank. Previously, I got scammed out of a win of a Code Forces round, so I want to do better this time. Okay. Now, let's see. V zeroed up first. While point is less than v dot size and q point dot first equal to targ. Remember to increment the pointer. So rec q point dot f, and we say vis l dot f l dot s equals 1, or it should be v, all v, and q dot push, it should be again that. Actually, this should just be v point. That works. Okay, now for each thing in the queue, so now we process everything at this distance. This is x dot f. Now, okay, we need the classic like grid stuff. Right. Rec x dot s minus 1, vis and r and c equals 1. Right. Let's see, this and what else? That x dot s minus 1 is greater than at nr and c. Otherwise, it's pointless. Need a semicolon. Okay. Let's see, make sure everything works. So we have this, it's all good. Put that in, sort them by decreasing order. Yep, well, not q.empty. Do the same thing. Yeah, okay. What? X.f. Wrong thing. Yep. First thing is the cost. That's just usually not how to do it, so I had it confused. Alright, so that's wrong. Why is it wrong? Let's see where we get here. So we don't even put that in anywhere. What? Am I like reading in the input wrong? Alright, so that's something that does happen. Somehow this is not working. Actually, this should be 0. That should be there. Should it be greater than or equal to? Okay, actually I should do this. While 1, if q.empty. Yeah. Actually, I don't need this at all. Cool. I don't understand why that is necessary, though. This should, at the very least, work somewhere here. This shouldn't fix it. If it fixes it, I'd be concerned. Okay, that doesn't change anything. Alright, 302. Now I'm so confused. So 401, 302, 300. Yeah, that's right. So 300. Okay. Now somehow it's this. So, what am I? Is this wrong somehow? It'd be nice to have things just work on the first try, wouldn't it? Okay. So we need to look at the second case. Second case is where it first goes wrong. So that's fine. 01. Better not be putting everything into the queue. That would be concerning. Good. Okay. So it's valid. Yeah, we can go there. X dot first is 3. So we should be in here. X dot f minus 1. Oh, wait, it's because I'm overwriting it. That's why. If this be point, all right. So if this L dot S okay, right, we do need this. We need to make sure that we don't revisit things. If we check and visited here, check visit here, we check visit here. Okay. Now we seem to be doing better. Now we get a psych fault. So that's not concerning. Okay, this is a mess. This is very much a mess. Somehow we're starting this at 4, which makes no sense. No idea how that could possibly happen. Unless I'm reading an input wrong somehow. Is that what's happening? Okay, psych fault, fine. Yeah, somehow it's 4. How would it possibly do that? Printing more and more things and getting more and more chaotic. Alright, so really, what is happening? So point, target, that. Okay. So we're good there. We put that in. We just print this. I don't understand how this is ending up in the queue. What are we doing here? Is this what's happening? I mean, there's no like multitest. There's no residue memory that's happening from here. I don't understand where this is coming from. Okay, so that's 300, right? Okay, now this actually works. So why does it crash now? Why? What is happening here? What is going on? Is it not compiling the right program anymore? Maybe I'm not running the right thing? Oh wait, okay. That's dumb. Okay, sure, but why is that happening now? Like, where is this coming from? Where is this 0, 0, 0 coming from? I messed up something here? I'm so confused. So the queue is becoming massive. But how? Where is this coming from? Okay, so if I comment this, is this the source? And stuff fixes it fine. If point is equal to v.size. Alright, so we create the target. This is gonna be some stupid bug, and it's gonna take like a second to fix, and everything's gonna be happy, isn't it? So if we've already visited this position, then increment the pointer and continue. I don't understand, like, what is pushing this into the queue? That breaks. That doesn't do anything. Like, where is this coming from? What is causing this? It's the same cell every time, too. Am I like overriding Q or something? Am I doing some weird thing that caused it to be screwed up? So DR and DC is fine. This is such a mess. This is such a mess. This is such a mess. So 0, 0, true. We're never in here again. Okay, I straight up just need to read everything. What the hell is going on? So if we've not visited this location yet, that should be enough. Every time we increment point. I guess the queue just infinitely sized or something. Is that really not something I can do? Seriously? been this bad at writing a BFS before, for Christ's sake. No, this doesn't even make sense. Does it do that at least? It doesn't even do that. It doesn't even print the thing. Push viewpoint. Like, I genuinely don't even understand where is 0 coming from. I'm popping the stuff from the queue. Where could this possibly be coming from? I'm not pushing anything into the queue here. Is this some sort of initialization problem? There's nothing here. It's like if I just get rid of this whole part. Could not comprehend what is causing this bug. So point is always at 3. That's never the problem. So here point is at 1. Which makes even less sense. Because this should be putting this into the queue. Actually, no, that does make sense. So that puts this here. What? 1 0 is not visited. Even if that were a problem, that wouldn't make sense. That wouldn't make any sense. It doesn't make any sense. It doesn't change anything. And every time we push something in the queue, we're setting it to be visited. What could possibly be happening? Alright, well there goes any chance of getting a good score, honestly. This is unbelievable. I'm not overwriting X. Using the columns right. So if valid, if not visited. If I get rid of this condition, does it fix something? It does not. So we set the rec to that. We set the visited to 1, so it has been visited. So what if I just make it so we can only go down? No point in going down a column. What if I just do this? If I set it so we can only go... No, wait, that doesn't make any sense. If I set it so we can only go up columns, does this fix things? There's no reason to ever go into a different row. Sure, this will make even less sense. Nope. Atrocious. I'll learn a whole lot of different vocabulary here. Q.empty. This is one of the problems of it being midnight. I just can't figure out anything apparently. I don't know what's happening. I can't write code. So this has not been visited. Guessing it has to be here. Is that what's causing this? Is that what it is this whole time? Yeah, it is. Okay. Alright, well that is a stupid perk of C++, I guess. That it just doesn't say anything. Yeah, alright. What else am I printing? So if I have an empty queue, it just dies completely. Somehow it just keeps trying that. Somehow it never broke, actually. Alright, well that's stupid. Alright, well, had that not happened, maybe we could have gotten a good rank, but it is completely over now. That's just everything. Okay. Just try and solve this last problem within any reasonable amount of time, maybe. And once in the ith row in the jth column is that. The checksum along each row and column. Might also be some problems with resetting things, but I don't think there would be. I don't know. Depends on test cases. And within the ith row and jth column is aij. Okay. Well, we got that. Damn. Alright. Guess there'll be more kickstarts. I don't know. So we go in each row and column, we take the XOR. Sure. So he remembers the checksum, he needs to determine when the matrix is not. Okay. Sure. N is 500. So we need to figure out when the matrix is recoverable. Let's see, 500. Okay. So let's see what we can do. So basically we have to figure out when are there not multiple matrices that do the same thing. How would that work? So if everything is present in at least one row, then... So if anything is present, if anything is by itself in a row or column, then it means we can determine it immediately. We can use the checksums. Otherwise it like matters. Does it matter what is what? Does that matter? Does it matter what the checksums are specifically? I'm not sure if it does. When can we immediately determine when a matrix is good? So we have some sort of set of values, right? And each of them is not unique on its row or its column. So then what? What does that mean for us? Yeah, let's do out some scenarios. Like say we have some shape like this. So like -1, -1, -1, -1, -1, -1, -1. And something like this. Right? Like, are these different inherently? Something like that, maybe. Are these different somehow? So, right, so say I make these values something, right? 1, 0, 1. So it means these must be different, these must be different, these must be different, these must be different. For example, this would be like 0, 1, 0. These must be the same, these must be the same, these must be different. And if I flip all of them, then they all work still. Say I have some random stuff here. For example, like say these are all 1 or something. Maybe like this. Then a solution is to set all these to 1. Are there more solutions? Yeah, like for example, we could flip this whole square and it wouldn't affect anything. Or we could flip this whole square and this whole square. So if we have any square at all, if we have any square like this, then we could flip it and we could flip all 4 cells here, get a different matrix, and it wouldn't change any of the answer. If we don't have such a square, then it means that there's at least one cell that isn't, it doesn't have the same row or column. So that has to be the condition. That like every cell must be on a unique row or column or something. Right, so like for example, we'll clear this whole top row except for 1. And then that will let us clear something there. Actually, in this case, clearing any of these will clear the whole thing, because that will let this one be cleared, then this one can be cleared, then this one, then that one, then this one, and also here. With higher costs, it's more complicated. But no matter what we're going to do, we're still going to clear everything in a row or a column. So I can read the input right. Not screwing it up like last time. I should read an N. What? I'm not sure if the checksums matter. I feel like they don't. Maybe they do. I should probably still solve the problem before anything else. So if we have such a square, then there's no solution. If we don't, then there is a solution. Because if there's no such square, then like for example, if this cell isn't involved in any square, actually, is it still possible for that to happen? Can we have some weird case? That's sort of interesting. Actually, I guess there isn't a square in here. But everything has at least 2, right? So actually, if we flipped all of these, it would be the same. It doesn't necessarily have to be a square, is it? It's more like if we can flip at least 2 things, or if we can flip an even number of things on each row and each column, then we can do that fine. Now, if each row and each column has at least 2 things, is that equivalent? Is that equivalent? What we really need to ask is there a subset that like does all this? The answer should be yes. Maybe the checksums do matter or something. Like if these checksums were 0, no. Um, it's also messy. So for n equals 4, we can literally just brute force it. That's not interesting. For smaller n, for n equals 40, what can we do? Okay, first I need the condition. We need to choose any subset of the negative ones, such that for each column and for each row, there are an even number of selected elements. Okay, let's say we pick the first 2 from each row. We know we have at least 2 in each row in each column. So we pick the first 2 from each row. Or say we're going to pick exactly 2 from each row. Or rather, if we have a 2x2 square, or not necessarily a square, it could be something like disjoint like this, then that's fine. That gives us the subset. Otherwise we don't, so we say we have something like this and something like this. Now, both of these have stuff in their column that we can still take. So why don't we take something from both of those? And for example, we have this and then this. Now in this situation, what can we do? Seems like it should always be the case. Actually, so we pick like any other one, right? So like, when we pick a row to satisfy this, we satisfy at least one of them. So we have at most one here. So either we finish this off, or we create a new one anyway. So at any point we have an even number of unmet requirements. And if we have another one here, then we would have a square. That has to be the case. Yeah, I don't know. Seems intuitive that we should be able to always do it. Because like, yeah, say we pick something to satisfy this, right? So we go here. So you have something else like this, maybe. And like this, and then maybe this negative one is over here instead. Actually, that doesn't work. Maybe something more like this. That works, I think. So right, then we take this, but it means we have a square. So if we ever like break it, Actually, at any point we always have an even number unsatisfied. But if we ever break it, it should imply that we have a square. Yeah. Yeah. Okay. This algorithm would work because if we ever get to a point where we have everything unsatisfied and we can't take any more, then it means that we have a contradiction with the fact that we have everything in one column, at least two things in each column. And if we ever have more than one in any position, if we ever have more than 3 in any position, or more than greater than or equal to 3 in any position, then we have some other thing unsatisfied, so we can remove whatever this row was, and then we would have even everywhere. So that would have to work. Yes. Okay, so the claim is, if there's at least one thing in every row, then if there's a row if there's a row or a column with only one thing, if only one -1, then we can immediately determine that -1 and we stop. Or then we continue. If at every point we can do this, then we're good. Otherwise, there exists some subset of the rows and columns that has at least like 2 or something. Yeah. And that means, what I was just trying to figure out there is that means that we always have multiple matrices. So, or multiple possible initial matrices. Right, so we just need to make it so we have at most one thing, and we can always do that. So now how do we do that? So we find our ending set. Then what? So for the first row, somehow we have to clear everything on that row. Either we do clear everything on that row, or we don't. If we don't clear everything on that row, it means everything on that row, like for example the first row, there are two possibilities. Either we delete everything on this row except for one of them, and then that one of them will be auto-deleted. So in this case, we basically just clear the entire row by itself, or we don't clear the entire row, and thus everything else from this row must be cleared through some columns or something. So basically it means that if we don't take this, then all of these columns must be the ones that kill this. Everything except for maybe the last one. Like for example, if we kill these two, then this cell is by itself on its row now, so we get that. So it's every column except for one of them, we have to kill everything. And that leaves some of the other columns. And then we consider that for all the rows, right? It's when is it profitable to do this? When is it profitable to do this, indeed? So take the smallest thing. Consider like the element with the smallest cost. Right? So then suppose it was auto removed. Then it means for everything on some of the columns or some of the rows, we deleted those. Can I contradict that idea? Okay, let's say we have, for example, something like this. So we have like 10, 10, 10, 1, 10, 10, 10. And so like consider this. Suppose this was auto removed. Then like either everything in its row or everything in its column is gone. But then like if everything in its row and its column is gone. Like I'm considering greedy here. I'm thinking that should be correct just because like if everything in its row and its suppose everything in its column is gone without loss of generality, whatever, right? So then if this was all deleted, then we got rid of everything else in its column, or they were all deleted or something. Like I think if we do this, then it should save us some other operation that would be of strictly greater cost. That's the idea. I think that should be it. Otherwise, we would have done some other operation. Oh yeah, whatever operation caused this thing to be deleted, then delete this instead of doing that operation, and it would follow whatever chain reaction there was backwards. Okay, that proves it. Yep, we should be able to do greedy. Okay, good. Is my mouse gonna work? Is my mouse existent? Is my screen frozen? Where is my mouse? Oh my god. Oh god. My mouse is spazzing out, but like I figured that sometimes the best way to fix it is just to like slam it onto the desk as hard as possible. Just very unintuitive. I don't recommend doing this. My mouse is so broken anyway that like I mean it could be very possible that the slamming is what caused it in the first place, but sometimes it just bugs out like crazy and goes to the side of the screen. When I eventually unplug everything and try everything again, it just works eventually. But I don't even know. I guess we'll find out. Okay, so, right, so for I equals 0 is then n I plus plus. So, count 5, 5, 5, 5. How many tests are there? 100, okay, so that's good. Okay, so, if mat I, this should be j. Thank you very much. J is equal to -1, add ij. am I doing this? Why am I making a function for something that's so simple as this? What am I doing? Dude, this is what happens when you have midnight brain. It's like, it's just crazy. Actually, wait, no, this does make sense. Because I need to add it to everything in the same row and column. Okay. And then save this for later. Alright, so Q pair Q. Okay, we're gonna do some other messy BFS stuff, and I'm scared. So this should not matter at all. The checksum should not matter. Right. So now what we're also gonna do is say we're doing like almost the exact same setup as last time, which I'm really scared about because you know how last time went. Spent like 30 minutes debugging something that made no sense. Alright, so it should be N, not M. If mat ij is equal to -1, v dot pushback By the way, that mistake has everything to do with me, just making a dumb mistake. It's unfortunate that it didn't tell me about how that error was going, but that was dumb. Should have figured that the Q was having some problems, but I don't know. Because Q.pop should be essentially like decrementing the pointer, and if it goes below 0, maybe it overflows or something. Not entirely sure. Okay, anyway, sort should be sort of akin to like creating a minimum spanning tree, which is kind of cool. So while 1, okay, I'm gonna be very careful about this now. If q.empty, let me consider some new thing. While point is less than b.size, if q.empty break, and so if mat, all right, mat l.f l.s is not equal to -1, continue. Otherwise, ants plus equals the cost mat l.f l.s equals 1. Anything that's not -1, q.push l. Right. Okay. So we should not have that issue again. That should be it, right? Yeah. So, okay. if I is not equal to R, then count RC plus equals D. If kill, and we have exactly 1, and mat RC is equal to -1, q dot push RC. Do the same thing here. All right, this should be, let's see, this should be I. Yep, do the same thing here, except we flip everything. So it's for the column. So count, oh my god, stupid mouse, RI. Right, so same thing, same thing, same thing, RI. Oh my god. Clean my glasses too. Okay, so what's going on? This is gonna be another 30 minutes of debugging one stupid issue. I'm so mad about that. Okay, nope, that's not what I meant to do. Let's get rid of that for now. Alright, so add x.f, x.s, subtract 1, and then do kill things. Is that the only problem? Or is add overloaded or something? We're gonna need some stronger tests, but this should suffice for now. Okay, well that's dumb. Alright, why is that happening? Matt. That doesn't explain everything though. Matt. Okay, explains some of the things. Oh, I see. So that saves that because I can go down here. I see. Okay. So actually that doesn't explain everything, but whatever. All right. So what's gonna happen? Oh, wait. Good. Count RC plus equals D. That is also necessary. That makes no sense. What? Oh wait. That is true. Mat ij is equal to 1. Yep, every time we push something into the queue, we have to set it to that. Okay, so that fixes that. Now what's with this? It should never be below 1, but just in case. This should never happen. If this happens, I would be so surprised, but I just want to make sure. Okay, good. So we go to 1. Then from here, say for everything in the same row, L.F, L.S. so the count here is 3. So we are resetting count. See out count ij. Oh my god. Come on. Alright. 3, 3, 3, 3. Yes, that is correct. Wait, no, that is not correct. That does not make sense. What? Oh, wait. Oh. Okay. Right, I need to do for each row and for each column. So it should be row, yeah. Good. That is a crucial mistake that I'm glad I got caught by the samples. Or count ij1 is also equal to 1. Put this in parens. It's not what I intend to do. Okay, so if it's valid and we have at most one thing here, then go here. Now this makes more sense. Now it should work. Now we're handling rows and columns independently. Now everything should be happy. Okay, that's good. So now let's make a bit of a better test. I guess we can do this. So 1, 3, 3, -1, 0, -1, 0, -1, -1, -1, -1, 0. 12, 15, 0. Checksums don't matter, so I'll just have that be anything. Should be 7. Good. Alright, make a bit of a stronger test. Do the same test I was thinking of. Here, that, and -1, -1, 0. Right? That's what it was? Yes, indeed. Make this here too, why not? So what's the best strategy here? We can remove the 7, remove the 8, that kills that. So we need to remove 4 things. So we remove the 7, the 8, the 9, and the 9. So that will kill this. So 7, 8, that removes this. 9, that removes this. And the 9, that removes this and removes this. Wait, what? So I remove this and remove this, and that kills this. Now we need to remove 5 things. Okay, so we can remove the 12 and that should work. So 7, 8, 9, 9, 12, 18, okay, 45. 36. How? How are we doing that? What's happening? Cout VP. No. What's happening? How am I doing this? So 7, 8, 9, 12. 7, 8, 9, 12. Okay, so where is this happening? Right, so we kill first 0, 3. rows and columns are the same, so that actually doesn't matter. Wait, what did I do? I changed it so we have a -1 here too. So we kill this. We kill 1, 3. So then the auto kills this. We kill 1, 2, which auto kills this. We kill 2, 1, which will auto kill that, auto kill that. Okay, that's a problem. Did I set up the cost right? I mean, I did, right? Yeah, 101. That should be good. All the things are 0. What have I messed up here? What am I missing? See how X and something's being removed even though it shouldn't. Okay, so okay, so it says we remove this. What? Row 0, column 1. Are you... What is it doing? What is it doing? What is it doing? What is it doing? What? 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 Okay, I mean, that should actually make a difference, but what? Actually, that printing doesn't make any sense. So 0, 3, sure. So many bugs this round, my god. I feel like we could have gotten such a good score, because the ideas were all not that hard. It's just solving them. It's just writing the code. That's frustrating. So 703, 0, 1. What did I mess up here? Am I reading the input wrong somehow? Oh, wait, okay, that's my mistake. Okay, there we go. So it should be 7, 8, 9, 9, 12. Yeah, okay. Alright, I messed that up myself. Cool. So, confused myself. If I had not done the debugging, it might have actually been faster, which is sort of unfortunate. Make sure this works. What did I just do? Just delete it. What am I printing now? Oh, we're good. Okay. Alright. Okay, let's hope. Oh, what? I submitted twice? Oh, well. If that's 2 penalties, I'm gonna be mad. Oh my god, that might be 2 penalties. That would be annoying. Wait, is that gonna count as a penalty against me? Because I submitted it twice. Can I like cancel this? Oh my god, okay, it's two penalties anyway. That's stupid. That is stupid. That is so stupid. I didn't think it had clicked. You know, Codeforces has a check for it says like you've submitted the exact same code before, so this doesn't happen. That's pretty nice of them. Alright, let's make sure whatever this is one. Okay, wait. First of all, multi-tests. That's not multi-tests, right? Okay, so we go until queue is empty. The only place we break is when the queue is empty, so we automatically reset that. We memset the count to 0 every time. We read in mat and we read in cost. So all of this is fine. From what I know, these don't matter, though maybe they do, whatever this wrong answer is. And yeah, I mean, okay, so 1, 5. -1, -1, -1, -1, -1. Say something like 0, 0, 0, 0, -1, 0, 0, 0, -1, 0. Why did I type that out 5 times instead of just doing that? Right, okay, so that dies, that dies, that dies, that dies, that dies. Alright, that dies. All of these two die. That dies. So we should have a cost of 1, right? 2. Okay, wait, so this dies, that dies. That dies, that dies. Oh wait, we do have 2 squares. This should make it 1. Yeah. Is that like a better way to do it that's not greedy or something? For the current thing, like either it gets auto removed or it doesn't, right? But if it's auto removed, then there's some operation we did that led to it being auto removed. And that caused some sort of chain reaction potentially. But we could reverse that chain reaction and instead remove this one and get the exact same removals. So it's like there exists an optimal strategy where this is auto removed, or where this is removed. So we assume it is removed, so we remove it. Then we still continue to see how that does, how that affects everything else, right? So we go through and decrement the counts for each row and for each column. We go into here. We change that row and that column. Plus equals D. If we're going to kill it and this count is less than or equal to 1 and the matrix is not -1. Set that to that. This is not equal to that column. Set that to that. Ri. Yep. Set the matrix to that, push it into the Q. Okay. So sorting this by the costs. Huh, maybe that's how the proof of Kruskal's works too. We say like if this edge is not taken, then there's some other sequence of edges that connects that node. Oh, that's cool. Okay, yeah, this is similar to the proof of Kruskal's, I think. The way that algorithm works. That's kind of cool. I should mention that later. All right, it is 1:40 a.m. so far. I really would not have wanted this to take so long. I guess that's what we're doing the whole night. Or at least for another. If I don't even solve this, I mean that's another possibility. So this matrix value is 1. Then we add it. We add everything on its row, on its column. We add everything on its row. So if it can be removed, we do remove it. If we have nothing, then we go through and again increase the costs and so on. We say while this pointer is less than the vertex on size, we say this is equal to, this is just like a storage, so I can increment this and then have this continue statement. So we go here, we take that. If this is already visited, then we don't use it. Otherwise we do use it because we're forced to. And that's what we use. Right, so now this will take the front of the Q. Guess we can do something like 1, 4. Do something dumb like that. Now what's the answer for this? Should be something like 9? Yeah. Okay. Do something like this. If we remove any 9, it should work, right? So it should still be 9. Wait, how does this work? Actually, it's not any 9. It depends on the ones we remove. What's the best way to do this? Okay, so remove that, remove that, remove that. remove that, remove that. That's not the best strategy, is it? So remove that, remove that, remove that. That kills that. Remove that, remove that, remove that. That kills that. Remove that, remove that, remove that. That kills that. That's what it thinks. But we can do better. We can do that instead. Wait, what? This is not optimal. Yeah, I know what the algorithm's doing. So we remove these. Remove these. Remove these. That's what it's going to do. But that's wrong because we can do better. For example, we can do this. So why does that fail? What fails about it? So the optimal answer should be 3 times 4 plus 4. This is 16. Right. So is this an implementation bug or... No, somehow it just assumes that all of these are necessary. Well, that is not the case. Is the reason because removing one thing could potentially result in two different things happening? If it's... So suppose this is auto-removed. It's better to look at it like this. Suppose... Yeah, that's easier to look at. So suppose this is auto-removed. Alright. So our strategy is going to be something like this, 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 then two of these threes. The optimal strategy is something like this, 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 and that. Now the question is like, suppose this is auto-removed, right? Then something happened to auto-remove it. So all the ones have been used, that's true. Now the idea is like removing this doesn't help us, right? Like say we remove all of these. So we now have something like, I'm going to use ones to represent not removed. So like 0, 0, 0, 0, 0, 1, 1. Right? So removing this is not helpful. Like say we remove something like this, that kills this. And that gets auto-killed by this. Okay, that is an issue. So the problem with the greedy is that it doesn't like encompass. That's unfortunate. That would have been a cool proof had it worked, but no, it doesn't. So yeah, the better way to remove that square is to not remove it. This could also extend to something like maybe like 1, 1, 4, 4, 4, 4, 1, 1. Alright, so if we make the same case, we'll use that instead. Should be the same issue, and therefore we can use the inductive part better. So we'll get 16. Answer should be remove these and all but this, for example. Then we remove this, it kills that, and kills that. We remove this, so we'll get 16, it should be 15. Yeah. Can we simulate it on a 3x3? For example, here. No, that's not helpful. That will get the right answer. Alright, okay, now I'm lost again. So, somehow we need to make it so we remove everything from a certain row and a certain column. How many people have solved this? It's an interesting question. You can use this as a indicator. Okay, a lot of people have solved this. That is unfortunate. We have 2 penalties so far, and both of them are wasted. They're literally at the exact same time. That's dumb. Actually, who won the round? That's sort of interesting to see. Nice. Not sure what's happening. Maybe I'm just missing something. Maybe that's the problem with doing rounds at midnight. So if we look at the first row, let me consider that idea again. If we look at the first row, yeah, then like for every column except one, we have to remove stuff from there. So it's like either we, for each row, either we remove everything from it or we remove nothing. Maybe that's an idea. Either we remove everything from that row or we remove nothing. If we were to remove everything, then what happens? Actually, if we remove nothing is more interesting. Right, then like everything from that row has to somehow be killed independently of others. And some sort of like two set or something. That's potentially a thing. Am I missing some constraint or something? So we'll pick some columns, pick some rows. So like first remove everything from the rows. So like we can do the initial BFS, sure. Then what? So now everything needs at least one other thing to be removed for it to be removed. So if we pick some row and we say sometimes it's not even necessary to move everything from a row though. Yeah, that's true also. It's like the question we get here is, does this even do anything? If something will later prove to be useless, maybe we don't need to do anything with it. Six minutes, man. What the hell? Wait, I'm sort of interested in something. I'm wondering, does it count as a penalty things that you didn't submit? No, it does not. So this does not affect my score. I mean, this is not hard. The first test set is not hard. I don't know how you would do the second test set. I don't know why that's easier. Hopefully everything's been working. If I've been talking to myself without a microphone for 2 hours, that'd be sad too. Just don't know what to do for this. Alright. What if it's like we delegate which ones to be auto-removed? Oh, that makes so much more sense. Oh, that's so much easier. Okay. We delegate which ones to be auto-removed. And then we remove everything else. And we can only auto-remove something if we don't already have something in its row and its column. Okay. That makes so much more sense. So let's do that. That makes so much more sense. Okay. Well, I guess that does it. Okay. Damn. I don't know what I would have done there. Plus count I 0 plus count I j 1. To be honest, I don't even know if I would have seen that idea when I was awake, so that's interesting anyway. So ants equals 0, ants plus equals cost ij. So put that here. I know it's a constraint the input, but I just want to make sure. Okay. So for if count l.f is equal to 1 or count l.s is equal to 1, ants minus equals v.f. is so much more simpler. That is more simpler. God, what am I even saying? That is so much more simple. More simpler. 2 a.m. man, does things to you. I don't know how well I'm gonna be able to explain this. I'm sorry if that just happens, but yeah, I'm gonna have to. Yeah, that's sort of scary. I'm gonna have to give some attempt to explain these solutions at the end. Oh my god. Okay, what? V down first. It's a pair. The first thing is a long. What? Pair. Oh. Duh. Okay. Not duh, because I didn't see it, but I don't know what I'm putting here. 0, 1, 1, 1, 1. Okay, what? Oh wait. No, we don't do that at all. Right. Okay. Good. This should be plus plus. Representatively sure, it doesn't actually matter in the end. We memset count at the beginning. So this is what matters. We should get the right 15 here. We still get 18. What? We still get 18. What? So we do this, we take all these. Maybe more things can be auto-removed. How much sense does this make? I'm not sure if it makes that much sense. I thought this idea was correct, but I also thought the other one was correct, so. Might be more than one in each row or column that can get auto-removed. For example, also if you've been following this whole time and don't understand, auto-removed is basically like we have only one in its row or its column, so we remove it by default instead of removing it via the person that's removing it with a cost. So we take those, now everything has 2. So some other things can be auto-removed is the idea, I guess. Actually, I don't understand this. I have a crazy idea now. Has something to do with crosswalls. think that's what we need to do. I'm so tired, but I don't know. Maybe this will work. I think it has a chance in working, so I'll just code it and then try it and then see if it works. It has something to do with minimum spanning tree. Init 2 times n. Right. Yeah. Okay. I have no idea how to prove this. Wow. If d.merge l.f l.s and it's minus equals x.f n plus. Right. So turn 0. Has stuff to do with cyclicity and min. So this is actually where Kruskal's proof comes in. Now it makes more sense to consider it like this. Yeah, there we go. Okay. Can't hurt to try it. This is a crazy idea. It's more of a guess than anything, actually. So there's still a potential chance it could be wrong. But I guess we'll see. I mean, it has a decent chance of working. Wait, what? Do we have a clarification? It is one after the other. I can't read this. Alright, well, we got it. Okay, that settles it. Alright, surprisingly not the worst rank, because I guess this is just a hard problem. Okay, let's see. We could have been one place higher, because one of our penalties was stupid. So how in the hell do you prove this? I mean, I guess it is like Kruskal's. Okay, sure. I don't know how to motivate this. I'm sorry to everyone who I'm going to explain this to. This idea that I had to solve it is just a byproduct of like just some craziness in general. Heck, Wall, man. 6 minutes to solve this. That's insane. These people are crazy. People are crazy. And Timmy too. Wow. Yeah. Okay. I guess it makes sense. If you have a cycle, then that's impossible. I said it was like minimum spanning tree, and then I just dropped that idea completely. Why did I do that? If I'd thought about it like that a bit more, then that would have just worked. Like that it would have just worked. So how do you think about this? It's connecting the row in the column. So some row's a leaf. Okay, sure. Well, Timmy's a god, so that's fine. 12 Tien. Yeah. Okay. Whatever. Let's just do this. So now I'm going to go over explanations like I usually do. And it is 2 a.m., so we're going to see how well that goes. There's a very non-zero chance that this is going to be an incoherent mess and ununderstandable to anyone. But I will try my best. Okay, in the first problem, you have essentially a string. Let's take, for example, A, B, C, a. That's one of their samples. And this is the first problem. So basically, we consider the score of the string the number of indices that, or the number of pairs of indices that are not, okay, wait. So we consider like for each index on the first half of the string, we consider like if this is x from the start, then we consider the position that's x from the end. So this is first from the start, and thus we pair it with the position that's x from the end. And then we gain a point if these are not equal to each other. So this pairing would give us no points because they are equal. For the second character, this is second from the start, so we pair it with the string, or we pair it with the character that's second from the end. These are not equal, so we gain a point. Basically, you want to change the string so that you have a specific number of points. In one change, you can change a character, so that, for example, I can make this into b, and I have a number k. For example, I want this string to have 2 points, and I want to find the minimum number of changes to do that. Okay, so first of all, we need to figure out how many points we initially have. We can do this by simply, for each character in the first half of the string, compare it with the other character. This is, for example, the character. For a character I, we're doing 0 indexing because that's how normal people do things. Then it will match with m minus I minus 1. So we compare these two, and we add a point if they're not equal. And then we do this for all I between 0 and m minus 2, not inclusive, because this will be the middle character. Actually, no. For an odd string, we would include the middle character, but because this is equal to itself, it's fine. It's not a problem. For an even string, it would not include past the middle. So n over 2 exclusive is a good upper bound. Or you can do casework based on the whether the length of the string is even or odd, but it doesn't really matter. So we do that, and we just find the initial score. Let this initial score be x. Then we want a score of k. So in one move, say we have a score of x, and say assume that if x is equal to k, then the answer is 0. If x is greater than k, then we need to remove some of our points. So if we have two things that aren't equal, we can, for example, change this character and then make it equal to the other character. Then this would decrease our score we have. So it would make it 1 closer to k. So we can do this while we have a pair that's equal, and because k is greater than or equal to 0, it means that x is always going to be greater than or equal to 0. And so if x is greater than k, then x is greater than 0, and thus there's always at least one pair that we can change to make it work. So if x is greater than k, the answer is x minus k. And it turns out if x is less than k, then we have a bunch of pairs that aren't equal, because k is also valid. K is a possible score for the string. So it's always going to be possible to do this. So therefore, because x is less than k, there are some pairs that could give us points but aren't. So in this case, we would, for example, change this to become not equal, and thus we would get a point out of it. So we can do this k minus x times, and then our score would be k, and we'd be done. So you can do this. Possibly you can merge these two cases into one, and then that handles it nicely. Or another way to do it is simply the absolute value of x minus k. And the way to do that would be simply so first we initially find the score. That's the wrong thing. This should be not equal to. And that's the initial mistake I made. That's why I got wrong answer. That's why you should read problems. And then simply you can use the absolute value function to do that. So the answer is just this. It's the absolute difference between the initial score and the target score. Yeah. Okay, for the second problem, we have a grid of 0s and 1s. Let me try. Can I draw this out? Is this going to be worth it? Yeah, why not? So 1 0 0 0, 1 0 0 1, 1 1 1 1, 1 0 1 0, 1 0 1 0, 1 1 1 0. Okay. We define an L as, first we pick some pivot point. Then we're going to, we pick some pivot point, for example here. Then we're going to take some segment either to the left or to the right, and we're going to take some segment either to the up or to the down. So for example, say we choose to the left and to the down. Then what we need is, for one of the segments we take, for example, let this be a segment of length x and a segment of length y. For one of the segments we take to be exactly twice the length of the other, so that it forms an L. So for example, either x is equal to 2 times y, or y is equal to 2 times x. So in this case, x equals 3 and y equals 4, so this is not valid. Neither of these are satisfied. However, if we took something like this, for example, if we took this as an L, let me get a different color. If we took only these two and then these 4, then we would have 2 here and 4 here, so they would be valid. And similarly, if we took this, it would be valid. And there are other things that we can take that would also be valid. So we want to figure out how many possible L's we can have. Or if we're given the grid, we want to figure out how many L's we have in this grid. Note that it doesn't necessarily need to be 2 and 4. It could be, for example, 3 and 6. This is also a valid L. So the way I've defined it is not the same as the way the problem's defined it, but thinking of it like picking a pivot and then choosing some segments that extend from this pivot is going to make it easier to think about the solution. Because now we know we have to have some pivot. Let's fix this pivot. Let's say we're going to choose this pivot, then figure out how many L's have this as their pivot. Okay, now how do we do that? Well, for a single pivot, there are 4 possibilities we can do. We can do to the left and to the up. We can do to the left and to the down. We can do to the right and to the up, or we can do to the right and to the down. However you handle this is up to you. It depends on the way you like to code things. What I did was not visible, apparently. Yeah. So what I did was I said, well, actually, it sort of depends on the rest of the solution, right? So say we fix some orientation. Say, for example, we're going to pick left and we're going to pick down. So what we need to do is we need to figure out how many possible L's we can make from this, from taking something from the left and something from the down. Now there's something else we can fix too, and in fact we actually have 8 cases here if you want to think of it that way. We have, let the left be, for example, x, let the horizontal one be like h, and the vertical one be v. Then we could have h be less than v, and therefore v equals 2 times h, or v be less than h, and therefore h equals 2 times v. Now for the smaller constraints, for example, for r and c are 40, we can simply fix this pivot, then directly like go over the possible values of h and v and figure out if it's valid or not. This would take either O of n cubed if you use a smart way of counting the ones, or O of n to the 4th if you literally just check if everything's a 1. That would give you some subtask points, so that's fine, but we can do better. I just wrote h equals 2 times h, so that doesn't make sense. Oh, and also like 2 1s is not a valid L. Like it has to actually look like an L. Like we have to have each of the segments, like for h and v, have to be greater than or equal to 2. So in this case, h would be 1, so that's not valid. Right. So assume without loss of generality that h is less than v. So this is shorter, this is longer. Then there are 2 possibilities. Like, oh yeah, so we let h, okay, right. So to figure out like how many L's we can make, assuming just like with this set of cases where we're going to the left and to the down, and then what we can do with that from this pivot, say we have a certain number of 1s to the left. So call this CH, and then we have a certain number of 1s to the down. So imagine like a streak of 1s. Where, for example, if we had something like this, and we were counting the streak from this position to the right, then it would only include this one because here we have a 0, and the L has to be composed of all 1s. So the streak here would be 2. So here, we let the streak here be, like, for example, the count of verticals. So there are two possibilities. We can make every L except for either when we run out of vertical ones or when we run out of horizontal ones. So how many horizontal ones, assuming only the horizontal part is relevant, how many can we make? For this, we can make we can let H be anything between 2 and the count of that and the count of that. Like, we can either have two ones or 3 ones over here. For the vertical ones, it's a bit different. It has to be either, so we have to count in multiples of 2 because we have to have, this has to be an even number so that it's twice this. So we can have 4, and then we can have 6 if H is 3, and we continue. So it can be up to 4 and CV where these are even. Right, so how many does this give us? How many, like, L's can we make from this? So this is an open interval. So for example, say this was 3, then this would give us CH minus 2 plus 1, or CH minus 1. Oh, wait, what? Yeah, CH minus 2 plus 1, or rather CH minus 1. Because this is just a normal formula for the number of numbers on a specific interval. So then for here, really we're counting from even numbers. So we have, for example, 4, 6, 8, up to CV or CV minus 1, depending on parity. Right, so because these are all even, we can imagine like we're counting the h's that correspond to it instead. So we can think of it like counting from 2, and then from 3, and then from 4, and then dot dot dot, and then CV over 2. So if this is a decimal, then like we can't count it. So really what we want is the floor value of this, and the floor of the floor of value x is simply, it just means round down. Like, the floor of 1.5 will simply be 1. And the floor of any integer is itself. So we can get any value for v between 2 and the floor of the count of verticals divided by 2. So really this interval becomes that, 2 to the floor of count of verticals over 2. And this gives us, using the same formula, this simplifies to the count of verticals over 2 minus 1. The formula is the same as this. I'll let you work out that exactly by yourself if you want. It should not be that hard. Sorry, it's 2:30. I'm not coherent right now. Yeah, so basically, the one that's going to limit us is the one of these that's smaller. So the number of L's we can make is the minimum of these two. Because when we can't make any more, then we're limited by one of them. So we have to take the minimum, because we need both of them to be valid. And if this is less than 0, then make sure not to count it. Like, we don't want to subtract from the answer. So it's really the maximum. So really the formula is the maximum of 0, because we need to make sure we don't negative. And the minimum of CH and the floor of CV over 2 minus 1. And again, these counts are simply the streaks of ones. So if we let this function be like f of like a and b, and so this becomes like, for example, ch equals a and then cv equals b, so it's the minimum of a and the floor of b over 2, which is sort of the way I did it. Then we can think of it like that. And then to handle all the cases, for example, to handle left and down, like right and down, and then this being less than, like this being the smaller one and this being the larger one, etc. We can do something like, for example, we can add up stuff like f of ch. So like f of the count on the left and the count on the down, plus like the reversing the variables, because either of these can be the larger one. And then we do the same thing for example, to the right. And then we do that for all possible cases. What I did was, I mean, it's something you can do. What I sort of did was I sort of merged both possibilities into one. So this handles both of them at once. This handles both, this being the smaller one and the larger one. So it just takes the formula and like it does them both at once. So then really all of this is just, this is like the same thing copy pasted 4 times basically. I'm just counting these runs. So in my code, 0 represents left, I think. I think. No. Am I wrong? I think I am wrong. Yes. Wait. For each row, for each column. No, 0 is left. Yeah, that's right. Then 1 is right. And then 2 is down, I believe. No, 2 is above. And then 3 is down. So then we need to call stuff like f of c0 and c2 plus f of c0 and c3 plus, this is a different f. This is the f that accounts for both possibilities at the same time, where this is both the longer one and the shorter one. So then f of c1 and c2 and f of c1 and c3. You can notice that, like, for example, these zeros are here twice and these ones are here twice, so you can loop these variables at this point. Like, you can loop from 0 to 1 and then map each of those with something from 2 to 3. So this is what I did. So like, fix the first one, it can be either 0 or 1, and then fix the second one, it can be either 0 or 1, and then it would map to either 2 or 3. So it's not the worst if you count it smartly. But either way, no matter what, there's also the possibility of just doing out all the cases anyway. So it doesn't really matter how you do it as long as it's correct. But anyway, yeah, working out formulas, stuff like that, math, woohoo. So this works in O of n squared. Oh yeah, and the previous problem is O of n. This works in O of n squared because each pivot is like sort of O of 1 to evaluate. If you really want to think about it, it's like O of n times like 8 or something because there are 8 cases, but asymptotically it's O of n squared. Alright, so these I may find harder to explain, but we can try anyway. So we have a grid. Let's say let's make a stronger case. We have a grid. It's like 3, 7, 4, 2, 1, 9, 3, 7, 2, 6, 5, 4, 3, 3, 2, 1. Okay, sure. And essentially what we want to do is, in one move, we can pick a cell and increase its value by 1. We cannot decrease. And then what we want to do is we want to make it so for every like horizontal or vertical gap, the difference between these two elements, the absolute difference is at most 1. So like, for example, here, the absolute difference between 3 and 7 must be less than or equal to 1. They can be equal, that's fine, but they must be at most 1 apart from each other. So we want to find the minimum number of moves it takes. So the fact that we can only increase is important. If we can increase or decrease, I think this will be a lot harder. But irrelevant because we can only increase. So we figure out, how do we do this? And alright, so basically consider this 9. This 9 is like the maximum element we have on the grid. If we increase this 9, then it means that like either we would increase some other things or we wouldn't, or we like, it's pointless to increase the 9 in general. Because everything, like, by definition, it's the maximum element. So we can leave this sort of unchanged. And then when we do, it means that everything around it... Okay, hang on. So it's pointless to increase the 9 because it's the maximum element. And so if we were to increase it, that means that the only reason we would have to increase it is if we were to match it with something that it's too small for, and therefore it would have to be at least like 11. But this is already the maximum element, so there's no reason to do that. So we assume this 9 is unchanged. Then what that means is we have a constraint on the neighboring elements. That all of these must be at least 8 to match with this 9 that we have. So let's make a new grid that sort of represents the constraints we have on each element. So of course each element must be greater than or equal to itself. So this must be greater than or equal to 9. So then when we put this 9 down, and we're going to put all 9s down at once. So then it means we're going to constrain some of these elements to be at least 8. So for example, this must be at least 8, this must be at least 8, this must be at least 8, this must be at least 8. So now what we've done is we're sort of saying, like, now we've handled everything that has to do with 9s. So now every 9 we have is irrelevant. In fact, let me go a bit further. Say we have 2 9s. For example, here. So now we put another 9 down. And then this must be at least 8, and this must be at least 8. Now every 9 is now irrelevant because we, by default, handled all the conditions that, like, go with an element. Or we sort of put down the constraints on the board to make it so every 9 would be, like, happy. Because everything adjacent to it is at least 8. And we never increase it past 9 because, again, it's the maximum, so there's no reason to do that. So this is gonna... Right, so now we're sort of, like, assuming that now, like, 8 is the maximum element. So everything that's 8 from the initial grid, which happens to be nothing, we would now put on the new grid. And then we would say everything next to an 8 has to be at least 7. And we would never increase it past 7 because if we did, it would be pointless. It would just make it harder to do everything else. So it has to be pretty much exactly 7. So now we can also put down all the 7s from the initial grid, of which there are none, because what that means is that, because again, every element must be at least itself. So now everything adjacent to a 7 has to be a 6. And so with this constraint array, we sort of just, we know that, like, this has to be at least a 7, and there's no reason to increase it to further than a 7, and it works if it's a 7, so that might as well be what we do. So it's fine if we do that, and therefore every element can be increased to exactly its constraint. So the answer then is for each cell, it's the value of its constraint minus itself. Like this, for example, would be 7 minus 3 because it's currently 3 and we need to make it 7. This would be 8 minus 7, this would be 7 minus 4, this would be 6 minus 2, 8 minus 1, 9 minus 9, etc. Note that some of them we don't need to do anything for, and that's fine. So the way this is going to work is, it's sort of like a breadth first search, if you've heard of that. Essentially, like, the idea is when we have a constraint for a cell, it means we're never going to constrain it higher. Because if we were to constrain it higher, then we would have already done so with some previous value. And the idea for that is that we visit values in descending order. Notice how first we visited all the 9s, and we put all the 9s down on the board first. Then we visited all the 8s, and then we put all the 8s down. And then we visited all the 7s, and then we visited all the 6s. Because every constraint makes it so, like, we go down 1. So if we visit a 6, we'll never go back up to a 7 because every, like, adjacency to a 6 will force us to put down a 5, which will not make us go up. So we visit everything in decreasing order, meaning that once we visit a cell, like say we visit this and it's an 8, it means that we'll never have to increase this again. And because we know this must be at least 8 already, it means that we're done with this cell. We're never going to change it again. So we visit each cell at most once to slap a constraint on it. So complexity for this ends up being O of n squared, although you do have to be careful a bit with how you handle the values. So really the idea is, an easy way to think about it is iterate from the maximum array value to 1. So for example, iterate from 2 times 10 to the 6th to whatever the smallest value is. So for example, 0. So for each value, first, we're having like a queue of unprocessed elements. So for each value, actually it's even easier than that. Yeah, it's even easier than that, but don't worry about it for now. So for each value, we are going to sort of put it on the grid and say that like we haven't like assigned the constraints to its neighbors yet, but we'll do that in the future. So it is a lot like it is basically a breadth first search where we essentially, for the value x that we're currently at, for every value x on the initial grid, for example, we look at this 7. We can look at this 7. This has been constrained to an 8. So if it's not already constrained, then it means that this element, it's okay to have this element be exactly itself. So set the constraint of this element to itself. In this case, we would not do this because we have a higher constraint. But for example, we would do that with the 9 initially. Set the constraint of its value to itself, then stick it into the queue of the positions that we're going to visit. So for example, now the 9s are in the queue. Then like for every 9, put the constraints on all of the adjacent elements. So for every 9, say that everything next to it has to be at least 8. Now, if the thing next to it is already constrained to be greater than 8, for example, if we had another 9 here, then this would be 9. And then these would be 8, and etc. But don't worry about that. What that means is that there's no point to add the constraint of 8 here because it's already been constrained to 9. So we sort of ignore that. But we constrain everything that's hasn't been constrained yet to be this minus 1, to be x minus 1. Now we've handled all the 9s, and therefore we've handled everything that's greater than or equal to x. So now we can go down to x minus 1. So we do the same thing for x minus 1. We look at all the 8s, and we say we're going to put them in a queue, and then yeah, we'll do the same thing. Everything that's a neighbor will be constrained to be at least 7. So now we have all these 7s, and everything that was initially an 8 on the initial grid, we would also consider that. So now we have all these 7s, and now we process the value 7, and we set everything that's not yet constrained to be 6, and then we go from 6 to 5 to 4 to 0, and that's it. Implementation wise, we can handle it like a thing. We can handle it like a BFS. We can use, like, for example, we can like sort the cells by their value, and then we can use sort of like a pointer on the sorted array to figure out, like, when we visit a value, we use the pointer to like look at everything that has that value. That's pointless. Like, for example, for everything, because it's sorted, all the all the cells that have a certain value will be together. So we use the pointer to look at all the cells that have that certain value, and then when it stops having that certain value, or it goes outside of the range of the cells, then we stop. But for everything that has that value, then we stick it into the queue. And then the idea is if some value is unvisited, or like, for example, here we don't have any 8s, which is unfortunate. Like in the initial grid, we don't have any 8s. But we do have things that are unvisited. Actually, this will never happen. I just realized this will never happen. There's no point to having this. This will never happen. So that's stupid. But I guess that makes implementation easier. Basically, yeah, we start at the maximum element, I guess, and then we can use the pointer to, so we can just like get rid of all this. This is all pointless. Really what we need is like, we just need like, when we're at a certain value, for everything that we haven't looked at yet in the initial grid that has that value, also consider that. Like for example, when we're at 7, we consider these two to be constrained to be 7. And when we start off with 9, we consider this to be constrained to be 9, and these two. And then we do that until we don't have any cells left to visit in the constraint grid. Okay, I'm not sure how well that was explained. This is not gonna, it's not gonna be my best video for sure. Taking an hour and a half on this. So like, yeah, we create a sorted list of cells that correspond to the position. So we sort them by their value, and then we also store their position. Sort them in descending order. Then we have a queue. I guess this happens once at the very beginning and then never again. This never happens except for at the very beginning. Also, this was my bug, this one line that kept me stuck for like 20 minutes. Right, but what we're gonna do is we're going to so for everything not yet visited in the initial value array that has the same value, we also consider that in the queue. Then for the current cell that we're at, we constrain all of its neighbors. So this is like DR and DC are basically like all the possible neighbors. And then, yeah, I'm losing my train of thought like every 5 seconds or so. Then we constrain all of its neighbors. So if you don't know breadth first search, you should search that first, or yeah, search. You should look that up because it probably helps you. Helps to understand this easier. But it very much resembles that. Except we also just, at the same time, we look at all these cells in the initial grid that have this value, and we put them all down at the same time. And the reason we need to do this is, for example, take this grid, like 9, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 7. Or like 8 or something, right? So that was pointless. But like if we only do the 9, and then we say that like the 9 is going to constrain everything, well, this 8 sort of has dominance over this region. And maybe even more. Yeah, it has dominance over like this whole thing. So like these are going to be constrained to fit the 8, and these are going to be constrained to fit the 9. So we need to also consider this 8 because it becomes relevant even though we have a greater element in the array, or in the matrix. Okay, yeah, I don't know. Maybe stare at the code for a bit if it's not the most understandable. It's also not the best code, so I don't know. I don't know. I don't know at all. Alright, this problem is the most fun one. And also, like, not the most fun one. Yeah, I don't know how to motivate this. Honestly, I just, like, had this as a random stroke of thought and it just happened to work. Okay. I'm gonna try and prove it because why not? But I guess I can have some attempt to prove it. So the basic idea is we need to figure out we need to figure out in what case can we restore the matrix. And we can restore the matrix if there's only one possible matrix that corresponds to the initial values. So the first observation is that when we have some, let's say for example, the first thing is that like the initial values don't matter at all, and neither do the checksums. So really like the last two lines of input don't matter at all, and we don't care if these are zeros or ones because we already have an initial way to satisfy it. We just need to know, are there multiple ways to do it or not? So for example, I'm going to ignore the values and treat everything that's not -1 as 0. So for example, we have 0, -1, 0, 0, 0, 0, 0, 0, -1. No, 0, 0, 0. Now the idea is we know the checksum for this row. We know that everything in this row is going to XOR to some value. So we also know the values of everything except for this one. So we just need to choose the value of this one to make this satisfied. And therefore this value is uniquely determined by the checksum of this row. You probably just gave us the checksums to be confusing and make it not as obvious, but yeah. Basically, when for some cell, if either it's the only -1 in its row or it's the only -1 in its column, then it becomes automatically like determinable. So we can say that it's like automatically removed kind of, or auto removed, which I'm probably going to be using as terminology. And so similarly, because it's the only -1 in its column, we auto remove it that way too. However, if I changed it a bit, so for example here, then this would be the only one in its row, but not the only one in its column. But because it's the only one in its row, we can determine it because we know everything else in its row has to be something. So yeah. Now if I changed a few more, now nothing is the only one in its row or its column. So what that means is there is not a unique matrix. Because for example, say these checksums for like 0, 1, 1, 0 or something. Then the initial values that would work would be something like 0. This is possible. 0, yeah, 0, 0, 0, 1. Right. Right? Yeah. Right? Yeah. Okay. Now the idea is if I flip everything in this square, I'm gonna use a different color. If I flip the bits of everything in this square, then it's also a valid matrix. You can validate these checksums yourself if you want. But the idea is because we have an even number of bits in each square, and flipping an even number of bits will not change the XOR, because XOR is like addition modulo 2, then it means that we have at least two different matrices. Different unique makes no sense whatsoever. We have two different matrices that both satisfy the answer and they both create the same checksum. So that's not going to work. Right. So the question is like, does this generalize? And the answer is yes, it does generalize. So consider like the initial state of the board. So we may, for example, have some rogue things that can be automatically determined. So for example, this is in a column by itself, so we can change this to a 0. Now after that, this is in a row by itself, so we can change this to 0. And yeah, so that's in a row by itself, so we can change this to 0. And now this is like the resting state of the board. Like it won't change until we remove something. So now we have the constraint that every row is either empty or has at least 2 negative ones in it. Specifically, not 1. Ah, my jaw. All right, so we can sort of ignore entire columns that don't have anything in them, or ignore entire rows. Or I just said that backwards, but we can ignore rows or columns that have nothing in them because they're irrelevant. So now we can assume that every row and every column has at least 2. Now I claim that when every row and every column has at least 2 bits, or at least 2 negative ones, there's always at least 2 different matrices. So it's guaranteed that there's at least one way to do it. So just assume we figured out the way to do it. It may be very complicated, it doesn't really matter, but we assume we figured out a way to do it. So what that means is what we can do is we can pick some subset of the negative ones to flip, so that in every row we flip an even number of them, and in every column we flip an even number of them. So what that means is that it doesn't change the checksums at all, because it changes an even number in each row and each column. So every checksum is the same, so the matrix is still valid. However, because we flip some of them, it's a different matrix. So look, proving this is not easy. It involves some contradiction stuff. Basically, the idea is you can do it by picking exactly 2 from each row and each column. Or you can do it by picking exactly 2 from each row. So if you ever have a square where there's 2, where you have 2 rows, 2 columns, and you pick 2 from each of them, then that's automatically valid. So if we have a square, we're done. It works, and that the claim is true that we have 2 different matrices. Otherwise, we assume that we have no squares. And so this is where the argument gets kind of harder. So for the first row, we can pick any 2 cells. For example, say we pick these 2. Now, for this, because this column has at least 2, there's some other column that also has this square filled in. So let this be the next column, for example. It doesn't really matter what order we're in. So if the other cell in this column, or this row has at least 2 as well. So if some other cell in this row has this exact column, then we have a square, so it's a contradiction. So either way, we're still already done. Otherwise, it doesn't. So now we have this. So now we can say sort of that this column is done because we have 2 here. So we're sort of good. And at every point, we have exactly 2 columns that don't have 2. Because at every point, we choose it so that we get rid of one of the columns. So now we change this column to satisfied because we choose so that way. And we can always choose so because every column has at least 2. And then either we get rid of the other column as well, and therefore all columns are satisfied, so we picked a valid subset that we can flip that has at least 2, or that has an even number in each row and each column, or we pick something else and we introduce a new column, and therefore we still again have exactly 2 that are that are waiting for more cells to be flipped so that we can have an even number. Okay, now the final step is to claim that while we have at least 2, then they're always of exactly one let's see, they're always of exactly one We always picked exactly one from each column. Like we can't have picked 3. That's not possible, because if we did, then we would have a square, is sort of the way we're going to prove that. So now, like for example, this row is done. Actually, it's not that we have a square. It's even easier than that, actually. So say we're now going to pick some from this column to satisfy this column. So for example, we pick this, and then now the only other thing in this row is this one, for example. Okay. So now we have this configuration where, well, it's going to be invalid because this configuration, the strategy we take is going to be invalid because the rows are going to be fine, but we have 3 in this column, 2 in this column, 1 in this column, and 2 in this column. And now the general idea is that we can remove whatever caused these to be both incremented, and it would still be valid, is the idea. That we could remove that. How's that gonna work? So we may not necessarily like have this to be exact, but there will always be something that we can remove to make it so these are even. Is it always exact? I think it might be. That's a possibility. Well, maybe not. I think like, I don't know. My brain is not working enough to be able to flesh out this proof fully. But I think like either like it's some sort of like chain reaction thing that makes it work, or it means we have a square, or it's like, or it means that this pair is always existent. There's always some row that has exactly these two things or something. I'm not entirely sure. But the idea is that we pick exactly 2 from each row and we find a strategy that always works to find such a set that we can flip and then change the matrix. And it's like proof by the fact that it got accepted. It always works. So anyway, what that means is that now we have to figure out a way to remove some negative ones and change them to, for example, zeros, with as little total cost as possible to make it so, like if we, for example, remove this, it will like chain reaction. It will remove this one because now this has exactly 1 in this row. It will chain reaction this one. It will chain reaction this one. And we have to do it so we remove all of them. Because if at any point we have at least 2 in every row and every column, or at least 2 are 0, that is if no row and no column has a negative 1, or sorry, if no row and no column has exactly 1 of the negative ones, and there's at least 1 negative 1 left on the board, then it means we have to do more removals. What did I just say? I'm just saying like, now the only condition is like, we have to remove all the negative ones is the idea. If we have some negative ones in a resting state, like the ones that can't be auto-deleted, or if we have this constraint that we have at least 2 in every row and every column, or a 0, then it's not going to be possible to have a unique matrix. So we have to remove it to make that so. Okay, now I have to figure out how to like, is there any possible way to like explain why this makes sense as a solution? The basic idea is, on this final matrix, we're going to say, for example, we have the like negative, like a wall of negative ones. The strategy we're going to take is we're going to pick the values that are auto removed. So what it means is we're going to choose some chain such that if we delete everything that's not in this chain, doesn't necessarily have to be contiguous either. For example, it can be something like that. If we remove everything not in this chain, so if we use the cost and we remove all the negative ones that are not in this chain, then when we're done, everything in this chain will be auto-deleted via some sequence of like we can determinants. Like for example, in this column, we can determine this because it's the only one in its column. So now this is the only one in its row. So now this is the only one in its column. So this is the only one in its row and column and row and column. In fact, we can even extend this chain by 1 by saying also, for example, here. I think no. Wait. No, we cannot do that. No, that's dumb. Yep, we cannot do that. My bad. Now how do we do this? So we have to have at least one cell where like we have to have at least one cell that we can auto remove by default. So either the row or the column is non-existent. And if you think about it like having edges between these cells, like if we add an edge between every cell in the same row or in the same column, then we basically need to not have a cycle. Because if we do have a cycle, then it means that we can like start here, go to a different cell in its column, go to a different cell, or go to a different cell in its row, go to a different cell in that column, and then continue, and then end up back here. Which means that we just took a path that has at least 2 in each row or each column that we visited, because we can always go from this row to a different one in that row and to a different one in that column, and etc. So if we have a cycle in this graph we create, then that's bad. It means we don't have an answer. It means that it's an invalid set of things to not be deleted. So we need to not have a cycle. Now the question is not having cycles enough? And the answer is yes, it is also valid if we don't have any cycles. And the reason is because it becomes a tree. And so the reason trees are nice is because they have leaves. So a leaf, for example, in this instance would be something that either doesn't have something on the same column or it doesn't have something on the same row, meaning that it can be auto-deleted. Now when we remove a leaf, because we have a tree, it means we'll have something else that now becomes a leaf. That's just sort of how trees work. So when we now have a new leaf, we can keep removing leaves until we kill off the whole tree. And therefore it's valid to have this as something that will be auto-deleted inherently. Or like auto-removed or auto-determined, or however you think about it. Yeah, so that is basically the idea. We need to form a tree. Now, okay, the issue is like doing this is weird because the way you form the tree is dependent on like the other cells you put in. So it's not the greatest way to handle things. But the idea now is that we can think about a different way to represent the graph. Instead of connecting cells within each column or each row to each other, it's equivalent to connect the row. I always mix that up apparently. it's equivalent to connect the row itself to the column itself. And then, so when we have a cycle, like for example, say we do have a cycle, like this, then this row will be connected to this column, which will be connected to this row, which will be connected to, wait, what? Did I just say it backwards again? I think I did. So yeah, for example, like if we think about it like sort of a bipartite graph where we have rows here, like we have rows here and columns here. And this is like column 1, 2, 3, 4, 1, 2, 3, 4. And I'll number them here too, just to make it easy to understand. When we're here, we connect the first row to the second column. Then for this cell, we connect the fourth row to the second column. When we're here, we connect the fourth row to the third column for this one. For this one, we connect the second row to the third column. For this one, we connect the second row to the fourth column. And for this one, we connect the first row to the fourth column. And as you can see, not very clearly, but we do have a cycle, because we can go from here to here to here to here to here and then to here. It's not visible at all, but it does work. Maybe this is an easier way to draw it. No matter what, we're going to have an intersection. I guess that works. Anyway. So it means we're going to have a cycle in this graph where we connect rows to columns. Look, I don't have a good motivation for this idea. Basically, I saw it in some other problem, so I thought of using it here, and then that worked. And I'm surprised that it worked, and I don't know why it worked. But I guess this is just a trick you can think about later if you want or something. Let me see if there's an intuitive way to think about like why you would ever do this. Well, certainly if you have a tree, then it works, because a leaf node implies that there's some row that's connected to, like, let's see. It means it's some row that's only connected to at most one column. Or some column that's only connected to one row. And so if some row is only connected to one column, then that means that, like, the only thing in this row is that column. Like, for example, say we only have this cell. Then the only thing in this row is this. What did I just do? The only thing in this row is this column, because if we had more connections, if we had more things in this row, then it would be connected to different columns. I mean, yeah, I can prove that it works. I don't really understand how you would think of it. Like, literally, I told you my motivation for this is I saw it in some other contest. Let's try it. Because doing things at 2 a.m., you don't get the most original ideas. Or 3 a.m. at this point. Although it was 2 a.m. when I did that. Alright, so connecting the rows to the columns. Do I have anything more to say? I mean, that's the solution. So the cost for taking a cell is the cost for removing it. And then basically now what we're trying to do is we're trying to create the maximum spanning tree of this graph, where each of these forms an edge. And so to find the maximum spanning tree, you can use any algorithm. I did Kruskal's, it just sort of works. Yeah. The tree part should be fairly evident. It's sort of just the idea of the graph. Yeah, I don't know. I don't know. Uh, I don't think I have much to say. Much more to say, that is. Could try to think of some motivation, but it's just not working right now. So maybe that's it. If I if there's some intuitive way that I think about later, maybe I'll like put it in the comments or something, or like the description or a pinned comment. Yeah, my brain is just fresh out of thoughts right now. I can't think of anything. Guess it's just like, yeah. Firstly, I need to understand this myself, and then maybe I'll be able to explain it better later. The idea is you create this graph where, for a single node, for the cost of removing it that's given in the problem, you merge the row it's in and the column it's in, and then you need to form a maximum spanning tree, and then the answer is the sum of costs minus the cost of this maximum spanning tree. Just because this is like, these are the things you don't remove via taking a cost of. There is probably some other way to do it that kind of makes more sense. I just don't know how. I guess the idea is like if you have two things in the same column, that means that those rows are sort of intertwined. If you have something in that row, then it means you can't have something in the other row. I guess maybe the way to justify it is saying like it sort of like handles everything you need to satisfy like the spanning tree condition or the connectability condition. So it's sort of like, it's not necessarily like you explicitly make the graph. It's sort of more like the graph sort of handles everything you already do about the spanning tree. I don't know. I'm not entirely sure. Something about it works. I don't really know. There's probably some way to like make it so every cycle can like be represented in this graph, and every tree can also be represented in this graph and stuff. I don't know what I'm saying at this point. Okay. Yeah, I think this is enough. It is 3 a.m. now. Woo. Alright, so 79th. Would I have done better without that stupid... Oh, 81st. Okay. Would I have done better without that stupid resubmission? How much better would I have done? So 222. 29. So 218, 29 would be my final penalty. So I could be like 77th. Alright, whatever. Not that much of a difference. Okay, that kind of sucked though. I should have done better. At least for this one, I should not have taken so long to debug a single thing. That just did not go well. And then this one did eventually solve. I don't really know what to say about that. Took me a while, but it's also like not that easy for me at least. So we'll see. Okay, I don't know much more to say. Hope you enjoyed. Hope you got something out of it, maybe. Not sure what you could get out of it, given my explanations were not that coherent, but I guess we'll see. Alright, goodbye.